everyone, how are we doing? Hey Jesse, how you doing? What should we do today? Chapter 14, after serving students at a college. Oh, looks like we're doing stuff with the mean. Get my sheets open up here. Got some mocha from Starbucks. All the mochas at the bottom. I don't know if you can see that. Can you see that on the camera? Yeah, you can see all the mocha. All the mocha went to the bottom. On a researcher investigates whether the mean cholesterol. Yes. So we know it. We're going to get started here in a second, but what do we have to do for all these questions? What are we going to do for every one of these questions? You know it. So get prepared as we get started right here. What are we about to do for all these questions? What are we going to be doing? Throw out some U-bot points. What do we have to do for all these questions? Remember, it's not about solving one question. It's about knowing how to solve all questions. So we're not trying to solve one question here. We're trying to solve all the questions at all times. Every single question will be solved if we can solve just a few of them. That is our goal. I know that sounds crazy. Be like, okay, we're going to be able to solve every single question. But we can. If we know how to solve a few of them, then there's just patterns to them. So what are we going to do? Notation. Write out our answers. And like, remember when we solve these, so probably a lot of people aren't seeing this part of the video. This goes out to my all-stars right here. If you're watching this part of the video. First question was, after surveying college students, let me get them both written down right here. And then we'll start doing them both. Remember, when you're doing these questions, you want to not even read what they're asking. I know that sounds crazy, but you want to think about what they're going to ask you and how you would solve it. And then you understand what you're doing. And then if you get to a question on the test, you'll know what to do. After surveying students, there we go, and a researcher investigates. Okay, here we go at the 23 marks. Step, whoa. 423, stat 201, chapter 14 quiz. Let's do it right here. Okay, let's go to the main screen. After serving college students. Okay. After surveying college students. Livestock. Hey, after surveying college students. Okay, so this one looks like an interpretation question right here. This is all interpretation. Don't read their interpretation. What do you need to do first right here before even reading their interpretations? We're going to have to do this here. I'm going to have everyone pause. We need at least one person in the chat to do this. And what do we need to do before reading any of their interpretations? Any of their interpretations, what do we need to do? So I want you to think about what you would do to make sure you understand the concepts in this question as we work it right here, but what should you do before looking at any of their answers? So we have something we've been using. It's over here. So I'm going to put this over here to the side. And there it is over there to the side. So there's a different question. Yep. So Kaylin or Jesse, I need you to come up with your own right here for 100 points. After surveying college students at a college campus organization calculated 95% control for the mean cost of food for one term. So they're calculating it somewhere between 1,372 to 1,562. Now the organization is writing a report and they want to know how to interpret this interval. I am 95% confident that the true mean cost of food, the true mean of, and then cost of food, just throw it in there. That's, I think, right there. Just throw cost in there, Jesse, 100 points. And that's what it is. The hardest part for people a lot of times is this portion right here. I think you get full credit on the test. The true mean, just cost of food. And then if you look right here, they're trying to estimate the true mean cost of food. So usually you can get the context right here. You could add in for one term. Jesse did that. So Jesse, another 100 points right there. And thank you, Jesse, for that recovery right there. Perfect job. Perfect practice right there. So when you think about this, what are we saying? And then what are they saying? And how does that differ? So now that we have our interpretation, we need to look at what they say. And so it's not about 95% of all students pay somewhere between this. It's about the average cost for students. So this interpretation is incorrect. The confidence interval is not about individuals in a population. Let's see right here. It's not correct. This interpretation is incorrect. Confidence interval is not about individuals. It's about the mean of the mean right there. 95% of the students sampled paid between this and this. Now, here's what's interesting. If we work with some data right here. Oh, there we go. I think I just put that on the screen. Yeah, I think I just did. Don't want to be congested. I'm going to show you some data right here really quickly. And cool. We don't have that data set. That's fine. And I want you to see how data looks. So if I go ahead and create, we're going to load a data set right here, red class data set, survey 10, and survey 10 has in it a variable called height. Now, height is just the height of students. So as you would think, if we make a histogram of height right here, you can see the heights of students go somewhere between the lower 50s to the upper 70s, because right here is 6 foot tall. Here's 5 foot tall. A lot of students are between 5 and 6 feet tall. So if we go here and do a t interval, this is how quickly we can do things in statistics, is we get a t interval. Now, do you think 95% of students are somewhere between 67 to 68 inches? So just yes or no, Jesse, do you think 95% of students have a height that is between 67 to 68 inches? Because that's the interval to estimate the true mean height of students. So I am 95% confident the true mean height of students is between 67.4 to 68 inches. So that's how quickly we can get a t-interval like that to estimate the true mean. So do you think 95% of students have a height between that? And we can literally go over here and graph it and look where 67 to 68, 67 to 68, it's going to be right about here. Does that look like 95% of the data? 95% of students have a height between 67, and I'm just doing a quick graph of this, to 68. No, that's not what this interval is meant to estimate. This interval is not about singular students. It's about the mean. Where is the center of this? And for like all samples of size, whatever, where is the center of it? Well, it's more of a sampling distribution interpretation for a moment right there. But no, it's not about individual students again. So the interpretation is incorrect. The confidence interval is not about individuals. One knows that we don't know what all the students, because once again, it's using the interval right here. And look, this is not about all the students. That's about where the true mean is at. And you can see the variation in all the students over here. You can also go to something like a summary of this variable, and a summary of this variable will show you the min and the max in the 5-number summary. So you can see all the students had a height between 52 to 78. So no, it's ridiculous interpretation right there. One is 95% sure that the students in the sample. So how would we know? So take a moment here and just think theoretically. So don't answer the number yet. How would we know what the students in the sample paid? We could look at the what? How would we know what the students in the sample paid? How would we know what the students in the sample paid? This is a good question to understand what we're doing right here. How would we know what the students in the sample paid? Look at the what? How would we know what the students in, because we can know what the students in the sample paid. We don't make intervals to estimate the students in the sample. The mean of you're right, because we're trying to understand the true mean, right? So we should look at a sample mean. So all we would do here is look at a sample mean. And kind of upper minus lower, that's the range of the interval. To get the sample mean, and this is really good stuff to understand right here. I think I still have, I closed down. To get the sample, you're really close, Jesse, with the answer right there. To get the sample mean is at the where of the interval. The sample mean, here's the upper, here's the lower, and the sample mean is at the what of the interval? The center of the interval, right? So here's the center, and for this interval, it is y bar, and then we go plus a margin of error or minus a margin of error to the lower. So it is y bar plus or minus the t statistic times the standard deviation over the square root of n, which is the standard error. So with this right here, we could actually know what the center of this interval is. So think about this. Here's my interval right here. So if I take these two numbers, add them together, so I'm just finding the average of those two numbers, divide by 2, and there's just a decimal difference due to decimal carrying in the background. but that's the center of the interval. Just by averaging the two numbers, you get the sample mean, which is the estimate, which creates the best guess of what the true mean is. And that's what we're doing. We're trying to think, well, we saw this from a sample. What is true for all students? So right here, you can see that we would know, and look, that looks like the center of the interval to me. You could confirm this by taking the two numbers right here, just adding them up. We add them up, we divide by 2, and there it is. So it doesn't even tell you that here, that, oh, there it is right there. It doesn't tell you that that's the center of the interval like some of them do with a plus or minus. And you could compute the margin of error just by subtracting one of the values from it. You can see the margin of error is 95. So 95 or 1,467 plus or minus 95 is the interval. 95% of all samples of students will have average food cost between... No, it's not about samples of students. It's about the truth. So that looks correct to me right there. Hopefully, wait, no, that's not correct. It's not correct. A confidence interval estimates the population parameter is a correct statement. This is incorrect. One knows that, no. The interpretation is incorrect. 95 all samples will have average food costs within 2. This, I don't really like where they go with this because this is a truth that they're pulling back to from sampling distributions. If we knew what the true population mean was, it is true that 95% of all samples will have a mean that is within this of the truth. This is a chapter 14, part 1 on test 2 question. Not a huge fan of that. Oh, wait a minute. Look at this. I want you to see that. One is sounds a lot like what? One is, or one can be, however they phrased it, sounds a lot like what? Yeah, got it. I am. Yep. I was a little afraid. I am 95% confident that the average amount right here, that the true, and average means right here, among all, average among all. See, average among all means what? For the what? Think of a P word. Average among all is the average for the what of students. Think of a P word right here. So they're not saying true, and they're not saying the P word, which I wish they would say. The population, exactly. The average among all alludes to the population right there. So that would be the population average right there, is between the interval blank to blank. So that looks to be correct. Hopefully we didn't make an error. We did get them all correct. So they like to switch up the wording. There are ways to say these answers, and that's why you can always debate if you get something wrong on the test. There are alternative ways to say them, but why do you think I give you, and this is the last thing I'll ask on this, and we're going to do your question next, Jesse. Why do you think I always ask you to write your interpretation and do it the same exact way each time where we say, I am this % confident that the true this, and true is very important because that means for a population. Why do you think I always ask you to do this each time exactly like this, same structure, same way, and you should be able to recognize little differences. But when you get to the test, you'll have a structure that you know how to use, and you'll have practiced it. I'm sparkling today. So you get used to it, and you have a template for the test. Exactly. So it makes the test a lot easier. I'm going to do one thing between this video. I'm going to look at my alpha key right here, because I've sparkled with this shirt. If you notice some sparkling right here, we're going to do a little... Yay, I got the green screen fixed a little bit. It's all these fine-tuning settings you got to do. I thought that was something not being green screen, but it was actually my glass right there, which is off camera. And so the glass is, you can see it looks weird when the green screen goes through it or whatever. So I thought that was I was like, why is that being weird? But I've got that cut out on this part of the video. So I was like, why is that not getting green screened? I think I like that you like, it looks cool, Jesse. Also the light in this room sometimes changes. So sometimes I'm illuminated differently and that causes issues. So anyways, that's got that. Let's do the next question right here. Thank you, Jesse and Caitlin. Got the office hours crew right here. The next question is a researcher investigates. A researcher investigates. It's not this one. It's a different researcher. There's a lot of researchers here. The fly one's interesting. That one has a twist to it, I think. What's a twist? A researcher measured? No, this is researcher investigated. Oh, is it this one? Oh, cool. And then we need more after this because we don't have any more questions. So we got to get another question going. Stat 201. Chapter 14 quiz. This might be a quick one. Let's find out. Is Mubot awake? Mubot is awake. Okay. A medical research. Yeah, let's do a medical researcher next. Here we go. So with this one right here, you got me covered. Nice. Thank you, Jesse. I'm sure, give a shout out. If you're watching this video right now, I want you to post a comment and just, say someone is awesome. You don't have to, I don't know. You don't have to put their name. I don't know. Put a comment on this video, slap a like on this video. I'm going to be like an old school YouTuber right here with comment, like, subscribe, do it if you want. Your call. Anyways, so a medical researcher investigates whether the mean cholesterol level among those who eat frozen pizza exceeds this. So they're wondering if cholesterol levels, which do get your cholesterol checked, your HDL, your LDL, high density and low density, the value considered to be at risk of health risks. The confidence interval is this to ooh. Why did I immediately say ooh? Why? They're trying to see if there's evidence the people who eat frozen pizza, and I'll tell you, that stuffed crust frozen pizza, oof, it's good stuff. I have had my cholesterol checked recently, and it was good, though. So, hey, maybe their research is wrong. But they're not estimating for one person, which I'm one person. They're trying to understand the mean of individuals who eat frozen pizza. So why am I all of a sudden concerned right here about the average person who eats frozen pizza? They want to know if there's evidence that the mean for the average person, which would mean among all people who eat frozen pizza, is above 220. So what do you notice about this interval? Once again, don't even read their interpretations. Just look at the interval. I am 95% confident the true mean cholesterol of people who eat frozen pizza is contained in the interval 228.9 to 244.6. What's bad about this for this right here? Why are we worried? Explain why this indicates a health risk. Well, we think the true mean cholesterol level is contained in this interval, and that would be evidence that the true mean cholesterol level is above 220. So the confidence interval is entirely above 220. Therefore, the mean cholesterol level for those who eat frozen pizza, and it's about the average, since it doesn't give us percent, we assume it's, Jesse, 500 points correcting Brian right there. We should probably never assume, but two, if we did assume, 95% is the most common interval. So 500 points correcting Brian right there. 95% is the most common. This does indicate a risk. So it doesn't give the percent confidence. You should always give that, because what if this is only like a 2% confident interval, or 10%? Well, then the 95 would be much wider, and then maybe they only did this study on like 3 people. Like they talked to their 3 friends who wouldn't even be a random sample. So then there'd be huge methodological problems with the study. So that's what we like to do, is we like to understand, when do we have good research? When do we have a good understanding? Researcher measured the pulse rates. Look at all the research we're doing right here. So good, quick question right there. Just understanding what a confidence interval means, and that this would be evidence that there is a problem, at least from that interval alone. So here, let's mark the question real quick. Oh, I've got the wrong things. Mark the question, and then researcher measured. So 1953, stat 201, chapter 14 quiz. Okay. A medical researcher measured the pulse rates of individuals. They made a 95% confidence interval. This time we have it. Waist size is next. This one, I probably need to remove, Jesse, because I think it's sampling distributions. Explain carefully what the software output means. Okay. Once again, Jesse, since you're here, I'm going to give the answer. So you can type it if you want. I'll give some points if you do. But I'm going to give the answer again. We don't look at what they write, because we need to know how to write our own interpretations for the test. So we look at the interval, and we say, I am 95% confident that the true mean pulse rate, because pulse rate is a quantitative amount, like how fast is your pulse, and then we could compare, like my pulse is 5 faster than yours. I mean, it might be good if it's like 50 or 60, I don't know. We don't usually want a faster pulse. So I am 95% confident that the true mean pulse rate, because it's quantitative, is contained in the interval, and then say the interval right there. We say it's contained in the interval, not that it falls in the interval, because fall is an active word on the truth, and the truth is what the truth is. Like this pen is right here, and the interval might contain the pen. The pen is not going to fall, like the truth is not active. So that's why we don't like to say the word falls. I think there's one question that uses it, and I always hate that. That's the way I was taught. Truth is not active. The interval is the active thing that we are creating, so the interval might contain the truth. I am 95% confident the true mean pulse rate is contained in the interval 68.78 to 72.659, right there, all those points. Now, the big thing to remember is sometimes we say mean, sometimes we say proportion, and sometimes we'll say difference between the means, depending on what we are trying to understand. So you always have to look at the context. Is it proportions? Is it quantitative? Is it the difference between two means, which is when you compare like maybe males and females' heart rates? You could. If you got points off for that, I wouldn't, like if the grader gave you like a 3 or 3.5 out of 4, you could message me and say, hey, Brian, I think I should get my points back, and I probably would. And I'll be sending out the sheet here very soon. Graders are almost done. I think we're one of the last classes to be graded, but they're going to get it done, and should be very soon. We know all the grades and any curve, if there is one. Explain carefully what the software output means. We are 95% confident the interval of this contains the true mean heart rate. See right here, they put this last instead of in the middle. Like, I am 95% confident the true mean heart rate is contained in the interval blank to blank. What is the margin of error of the interval? Now, don't try to calculate it yet. Remember that the margin of error is always... Can we graph that? Yeah. Oh, we should do that because I took a picture of it, right? Yeah. We should find the class where I showed it and then look at that too. The margin of error is always what? The length of the interval, Jesse. 4-letter word. The margin of error, these are the margin of errors. This is the length of the interval. So the margin of error is always half the length of the interval. So you don't want to try to memorize stuff. You want to understand it theoretically, and then you'll know how to get it. So that way you're not like memorize. I mean, you memorize, or maybe you understand. You got to kind of memorize it, I guess, that the margin of error is half the length of the interval, like it's a plus or minus, which creates a symmetric up and symmetric down. So with it being this symmetric up and down, we can just take half the length of the interval. So how do we take the length of something? We just take its distance. So we go here, we go upper minus lower, and then we divide it by 2 for half the length, and that is equal to a margin of error. Do note that there are other formulas like upper minus center or center minus lower. Anything that would get you that purple region right there is going to get you a margin of error. So there's other ways of doing it. And of course, if you do lower minus upper, it'll just come out negative, but it is a plus or minus. So as long as you get the length, you're good. But don't enter in a negative because we just consider it like plus or minus this amount. So we got some crazy numbers, round to 1 decimal. So I think if you actually go right here, and you don't even need to enter in all the decimals, 72 point, because we're only rounding to 1 decimal, so let's just carry 3 in the calculation. Does that make sense theoretically, Jesse? Because we're only rounding to 1 decimal, so 194. I'd carry 3. 2 probably would work, but if it says round to 1 decimal, like you don't need to carry every single decimal. Okay, so this is where we learn from chapter 5. A lot of what we learn is going to stack on top of itself, and that's why I tell people, like, the better you learn the earlier chapters, the easier the later chapters are. So when you think of your empirical rule, the 68, 95, 99.7 with 1, 2, and 3 standard deviations. So now pretending you're saying 68, 95, and you went back to 90, you would make a Wetter interval. So if you were going 68, which is 1 standard deviation, 95, which is basically 2, 1.96, and then you went back to 90, where would you go? You'd make a Wetter interval. So if you, and these are T's technically, it'd be smaller. Yep. Smaller. And we'll view this visually right here, and then we'll do the next question. I think, did you give another one, Jesse? Just to view it visually for people to understand, because I think a lot of people understand this when I'm doing that, but I also want people to see it visually right here. If we were doing a T, first thing we would need to know is the degrees of freedom. So we have to come up with a hypothetical that they talk to 100 people, which would be 99 degrees of freedom. That's just hypothetical. I'm saying, maybe they talk to 99 people. Waist size question. You got it. You said, thank you for reminding me. And so now if you look right here, they made a 95% confidence interval with a T-score of basically 2. And then we go back to 90 and watch the interval. As I go towards 90, the interval gets smaller and the T-score gets smaller. And that 99 degrees of freedom was from a hypothetical idea that they did this study on 100 individuals, which the question doesn't say, but you always need the degrees of freedom when doing a T, And the formula for the degrees of freedom for a one sample t, when you're estimating the truth for one mean, one sample t, is n minus 1. So I pretended that they did it on 100 people because I have to know the degrees of freedom to talk about which t we are using and get the t value. Good stuff right there. Waist size question. It's good review stuff. Let me see this question. I saw it earlier, and I was like, I don't know if I like that question. I think it's towards the end. Chapter 14 quiz. Turning into my buddy Jason. Oh my gosh, so many researchers. I bet one person wrote all these researcher questions, Jesse. They were just like, a researcher's doing this, a medical researcher, an internet researcher, an advertising campaign. Yeah, just like someone was like, so a researcher measured heart rates, a researcher measured cholesterol, a researcher measured this. Okay. So this one's doing the central limit theorem right here. And so the central limit theorem is the idea that distributions become more normal and tighter as we increase the sample size. Very huge for statistics. Oh, flight. This is a good one right here. The chance of flights. Yeah. I think someone shows us summary statistics. So here, let me grab that question. And we'll do this question here. Oh my gosh. There we go. Okay. So when we do this question right here, the central limit theorem makes life easy for us. And I want us to think about what's going on with this. If the average height of a guy is 68 inches, let's say, if you talk to one guy, how tall would you expect one guy to be? So the average guy is 68 inches tall. If you talk to one guy, how tall would you expect the one guy to be? You just go, not saying he is this, but you just go talk to one guy. How tall do you think he might be? 68 inches. If you were to talk to 5 people and take the average of their height, you would still expect it to be 68 inches, or 2 people, or 10 people, or 20 people. And that's because the central limit theorem says that the mean stays the same. So because this would be the average of 2 individuals, the average of 5, the average of 10, the average of 20, and it would still be the same expected amount on average. Like we would expect to see this on average for an average of 2 individuals. And that's the mean of the mean. So it's the mean of the sampling distribution of the sample mean. Woo! Woo! That's a lot of words. Just means if you talk to 2 people and took the average of their heights, we're pretending this is heights, then you would expect to see this on average. Now, what does change is the standard deviation. And the standard deviation is very similar to the previous formulas that we've seen in multiple chapters. There's a standard error right there. But we're thinking about this right here. Now, there's a small change to the formula. This is the standard error. When we know the truth, we use the real standard deviation. And we divide by the sample size to get the standard deviation of a sample mean from a truth. So this is a truth right here. And this is the difference in the notation right here between the standard error. The standard error assumes what? What is the difference between the standard error and a standard deviation of the mean? And there's other questions that kind of go into this. So it's a good, like, what's the difference thing? So I do kind of support this question a little bit, but the standard error comes from a estimate of what the population is. The standard error. So here's what's really confusing, Jesse. This is like the super understanding of it. When we do P naught times Q naught over N square root, well, remember the null hypothesis is that P equals P naught. So we've assumed that this is P. So we've assumed that we've calculated a what here? Have we assumed that we've calculated a standard deviation of P hat? Or have we assumed we've calculated a standard error of P hat? So since we've assumed P equals P naught, and P is the truth, standard deviation, correct. That's why it's like, wait, why is that a standard deviation? Well, it's because we assumed P equals P naught, so we're assuming that is the truth, so we assume this is the true standard deviation. My dad had to explain that one to me. I was like, what? I was like, but we don't know that. And he's like, but we assumed we know it. I was like, why would we assume that? And he's like, null hypothesis. I don't know. Statistics is interesting. The standard deviation right here is going to get smaller, as we saw sigma over the square root of n. So I do like to solve this one a little bit of a cheat right here in R. So make sure to do this one in your calculator. We have here the sample size. So what I do is I go square root of the vector. I can square root a vector, right? 2, 5, 10, 20. There's the square. My sample size is square rooted. And then I'm going to take the original standard deviation of 4.002. And I am just dividing by those values. Does that make sense right here, Jesse? I can just show it this way too. Do each of these in your calculator, and then it asks you to round them. Yep, so just do it in the calculator, like 4.002 divided by square root of 2. I'll do that one for you. You have to do square root of 2, and then do 4.002 divided by that, and there's the answer. It says round to 3 decimals. So what's really great about doing code is you can just throw this in a round function. The parentheses make it a function, and that's the argument, round to 3 decimals. So I've got all the answers here on my other screen. I'm just going to put them in right here and not add the space, which I've done by accident before. And this helps ensure that I just get the question right, so I don't make an error. But that's how we can do things really quickly using code. Makes life easy. And then you don't have to worry about rounding, because if you ask software to say, round this to 3 decimals right here, so I said, take what I calculated and round it to 3 decimals. And just so people can see, it's a lot easier if I go to answer, store it as my answer here, and then we just say, take my answer, and really, we put the first argument as my answer and round the answer to 3 decimal. What did I do? Error in symbol. Oh, I got something extra in here. Oh, we're missing a parenthesis. Somehow I deleted a parenthesis. There we go. Okay, cool. Coding. We love coding. I love coding. Okay. How close are the values? Well, here's the thing. The central limit theorem is a theorem, and theorems are true. They are mathematically proven. So when you look at the actual values right here, which they give you a table, this is via simulation, so I shouldn't say actual. They are pretty close. Now, they won't be exact, but they're going to be pretty close. Remember, the mean will stay the same, and the mean basically stays the same. The standard deviation gets smaller as the sample size increases. And you can see this by the distribution getting tighter. Here's the individual values. Ooh, it's pretty normal to begin with. Oh, no, it's going to be 5, right? There's very few I can sometimes get wrong. Hey, Taylor, good to see you here. All the values are reasonably close because the central limit theorem is a theorem. Using a sample size of 5, and the reason I'm saying that is because it's mostly normal here. Little bit of a skew here, like tiny skew, normal. It's either going to be 5 or 10, and this is a kind of not fair question. Since this is the smallest sample size when it is unimodal and symmetric. Okay, I am a little worried about that one, so don't click that one yet. 5 looks to be correct. 2's not horrible. It's basically normal to begin with, but 5 looks this has a tiny bit of skew. Yeah, it's not horrible. I'd be like, that's basically normal. What about the shape of the distribution is our choice. And so without reading their answers, why was I saying it took such a small sample size? Because the original population is what? And this kind of goes towards large enough n. So this is a good review because we are doing the large enough n right here via the central limit theorem. Like this is all a conversation about large enough n right here. So why did it not take a very large n? The original data at the top, homework's 10 and 11? Yeah, good question, Taylor. The original is nearly normal, exactly. And so that way, and the problem with the newer questions we've been doing, as we stated yesterday during class, is we don't know the shape of the parent population. We could only estimate it from a sample. So there's the kind of more in-depth, well, we don't usually use large enough n. And sadly, we would have to have a decent size n to estimate the shape of the parent population. So the answer is going to be the distribution weight size nearly unimodal symmetric. I hope it's not highly skewed. No, we don't say regardless. That's pretty easy because regardless of, doesn't matter. Regardless of the distribution of waste, no, we need to look at it. So we should, yep, yeah. Some of the answers are just ridiculous. Like regardless of the distribution of waste size, no, we'd never say that. Regardless of, no, we'd never say that. It's highly skewed, no. So by process of elimination, it has to be this right here. The distribution of waste size is unimodal and symmetric, so the sampling distribution of the mean is close to normal even for smaller sample sizes. And it's a little bit mean because I could show this to a bunch of statisticians, and I bet some would say 10, and some would even say 20. 20 is being very careful. It's just the smaller you go, it's kind of like you wouldn't go to 2, I don't think many would say. I bet a lot of statisticians would say 10. 5, and then 20 in that order. I'd love to show this to 100 statisticians. Like I want to post this on like Reddit and be like, at what point is it normal? And I'd love a vote. Maybe I don't know. I don't know if I can do that. But that'd be pretty interesting to find out what 100 statisticians said on that problem. Because I bet you there's variation on it. Because it's true that it just becomes more normal, but then some people have a higher standard because when is it nearly normal? Well, it's never actually truly normal, but that's why we call it nearly normal. So yeah. And then we'll do flights on time and then Taylor's questions. Flights on time. Oh, we clicked it right away. Okay, so let me mark the question. It's funny because I think one thing my Pearson has a hard time doing is there's some ambiguity to statistics. Like statistics isn't about certainty. It's about, well, yeah, 10 is probably good enough. 20 would be better. So in statistics, we don't say we know things. We usually just say we have good reason to believe something. Like we would have good reason to believe it's normal at 5. Like if I was writing a test question and someone had to answer if it's at 5 or 10, as long as they justified it, it'd be fine. What are the chances of your flight leaving on time? So the first thing we see here are conditions. Now, what's interesting about this is they did a histogram providing the percent of flights on time for each month. Now you have to be careful here because how did they collect the data? So Jesse, this is a very tricky question for this reason, because did they ask, was a flight on time, or did they ask what percent of flights were on time each month? What did they ask? And this is why I've had people say, well, isn't this a such question? Because you're saying flight on time, right? But they didn't ask, is your flight on time? The question asked was a what question? It's why we can make a histogram. It's why we can get that value right there. So this is all very important to this question and understanding why it is not categorical, because they looked at a month and it's quantitative, right? And they said, what percent of flights were on time this month? They didn't say, was that on flight on time? Was that flight on time? Was that a flight on time? And then you could subtract from one month to another the amount of, or the percent of flights on time. So it's a little confusing because was a flight on time, but it's an aggregate telling you the percent of flights on time. And then we could look at the average percent of flights on time for a month, which makes sense. So it is quantitative, even though it kind of sounds odd, like percent of flights on time. It sounds like we're saying like, was a flight on time, but it's for that month. And then we could compare months. Let's see right here. So the assumptions are going to be, so ready for it? I know people here have practiced this. Condition 1. So I'm a little worried about the randomness because I am a little worried about that. It's a time series is the issue. This is a time series question. I wish they just gave me the monthly data and I could run the time series and make an ARIMA model or something. Doesn't say random here, does it? There is no, oh, here we go, right here. There is no evidence of a trend over time. So they're trying to tell you right there it's random. Like I literally said time series, and time series is about time order trend. I think they're going for that. Once again, issues with my Pearson, because does it have white noise? We don't even talk about white noise in Stat 201. So I'm going to assume that I'm a little worried about that. Don't click that button yet. Once again, the conditions are random, less than 10% of the data, which this is basically a non-finite population. And then the last condition would be nearly normal, and it looks like that's nearly normal. We have 270 observations, so even if that has some sort of skew, large enough M would state that the distribution of the mean would be more normal and tighter. So we're probably pretty good. Now we need to mark our notation and solve the question. But where are most people going to get stuck on making this 95% confidence interval, Jesse? Finding the what? And so drop the link in the chat. Most people are going to get stuck, and then some people are going to have a decimal difference, and you'll technically be wrong. So I can't correct this one. I might be sending, oh no. If I've sent you this part of this video, I apologize. If you've said, wait, I was just a few decimals off. We need to go here to the apps, and I can tell you about what the number will be off the top of my head. It's going to be a little, this is 95% confidence, Jesse, so it's going to be a little bit bigger than what? It's going to be a little bit bigger than what for 95% confidence. Now make sure you've clicked over here to the t distribution, go to between, go to your question. You see it has 270 sample size. So we should mark our notation on here. And with 270 sample size, degrees of freedom, and that's 269. So 269 degrees of freedom. And the value is going to be like I'm going to guess, ready? 1.982. That's my guess. And the answer is, let me throw an extra decimal. Darn it. Mouse close. It's basically 1.96. I know you're saying, you're like, well, wait a minute. 1.96, that's easy. Just use that. The t is used for a reason because it has extra uncertainty for smaller sample sizes. And this is a bit of a bigger sample size, but William Gossett made this distribution which calculates things accurately. I wasn't perfectly, my guess wasn't that perfect today. I should have just said 1.96, but a little bit bigger. And that's basically what it is. Check out our other videos where we go into more depth on the t. And it was 1.969, right? So t equals 1.969. You can probably good to carry 3 decimals on that. And then we go y bar plus or minus the t. The star means relative to the confidence. S over square root of n. We go right here. I think this gives you a lot of decimals, doesn't it? Yeah, it does. 78.111. Go. And so first thing we calculate here is the standard error. 270 divided by, or 5.16 divided by square root of 270. There's the standard error. Carry all of your decimals in your calculator. I'm just rounding for the purposes right here. This is going to become the margin of error. So the margin of error is going to be times 1.696. Margin of error is 0.5177. And there we go, 78. And now we go right here. And we go 78.111. And we're just going to add and subtract this number. So let's do it. And let's go right here. Plus that. 78, 2 decimals, 78.69. And then minus 77.59. Seems right? Right there. Now, interpret. Just start out the interpretation for me, Jesse. Just start it out, like the first few words. You don't have to give the full thing. I'll give the rest there. And look right here. Look at this. Look at that. They even put that right there for you. So we can just use that when we say it. So we just start out with, I am 95% confident the true percent of flights that are on time, that depart on time, is contained in the interval 77.59 to 78.69. There is, look at this, look at this, look at this, look at this. Look at this nonsense. Okay. There is a 95% confidence that the probability of a given flight. Nope, that's about singular flights. We're saying the true percentage of flights. There's 95% confidence that the interval contains the true mean. That sounds decent. There's 95% confidence that the probability of all flights departing on time will fall in this interval. I don't like the fall word. There's 95% confidence that the true mean monthly percentage of on-time flights. Okay, what's the difference between this one and this one? It does have the fall word down here. I think that's what they're getting at. What in the world? Are they saying we didn't? 0. Did I calculate my interval wrong, Jesse? Did I do something wrong with my interval? Let's see right here. What did I do today? I completely failed you on this question. The sample is neither a random sample nor from suitably randomized experiment. And then the interval is wrong. Hey, Philip, you came just in time for me to get the question wrong. So what did I do wrong on the interval? The interval, it looks like the interval is wrong for us. No, the interval is wrong because I got it right. Okay, so the interval is wrong. What did I do wrong on my interval? So we only got one thing wrong, I think. I calculated the interval wrong too. You saw the 0. You didn't see anything, Philip. You didn't see anything. Let me look at the numbers I used. 5.016, square root 270. Don't tell me they wanted like way more decimals on the t. 88219. What did I do? First question I've gotten wrong a little bit here. Wait, did I write down the t wrong? $500 who sees it? So I only missed one thing. It was the randomization thing. And then I just can't math today. I like flipped the numbers. Yep. Math errors. Did I give the 500 points? Not yet. There we go. Great job, Jesse. Okay. So math errors, our favorite thing on the test. Favorite thing, way to get a question wrong. So we only missed one thing. It's like I said to start. Of course, yeah, but they're literally having you do a problem that they're saying you shouldn't do. They're like, oh yeah, well you shouldn't have done this anyways. And then they have you do the winter one about snowfall. And they never mention conditions about that. Not 1.96 though. Janeki, good question right there. Not 1.96 though, because this is the T. It's very close to 1.96. And we could show here we might get it wrong if we do 1.96, but it won't be 1.96 because this is the T, and that's usually where a lot of errors are made. I just couldn't write down the number properly. So this is just this, I believe, around to 2 decimals. Yeah, we have a new law, chapter 14 right here, and I totally fumbled a question. No! I used the wrong T. So plus, I think it's just 0.6 right now. So there's that. And then minus 0.6, minus 0.6. And this should do it. I think we can redo it because I want to show you. There we go. Use the wrong T. Now, if you had gone in here, and I do want them to say it's wrong if you do this. If you went in here and just used the Z, this is not correct. Let's put here wrong. Someone might be doing this now. It should tell you you're wrong. So let's put here wrong. So this is wrong right here to use the Z. Do not use the Z or you will get it wrong. So let's see the work right here and see what happens if we use the Z and see if it gives us the wrong answer, which it should, because we shouldn't use the Z right here. This is a very common error. Once again, if you hit this error, you don't get points back. No, I'm hoping it should not accept this answer because this is theoretically wrong. Wow, I think you might actually get it correct because that rounds to 0.60. It's just because the sample size is so large. So you luck out on this and you don't get to see the small difference. So yeah, you would luck out on this because that would round to 0.60, which is what we found. But the reason the answers are so close is because why? For 500 points, the reasons the answers are so close here and you luck out and you get it right using the Z, which you shouldn't use, but you do luck out, is because why? Why do you luck out on this question and get it right using the Z? Because the answers are super close. Why? So you would luck out on this question using the Z by accident. Yeah, the N is exactly. Very large sample size means, boom, Jesse, exactly. So you luck out because at a large sample size, the Z and the T are virtually identical. There's the T statistic, and as degrees of freedom increase, it goes towards 1.96. Start with 1 degree of freedom and start increasing it, and you can see it approaches 1.96. So after exactly, so N minus 1 At some point, it's basically 1.96. Like we can start adding in nines, and it gets super close to 1.96. Only at infinite degrees of freedom does it reach 1.96. So it never actually reaches it. And I do need to contact Adam Spanbauer. Huge shout outs to him, because there is a problem where this is going below 1.96. Wow, look at that. I had to ask him, and look what just happened to it. You'll never have sample sizes this large, but oh, I should show him that. That's weird. He might need to put in a cap for the numbers. Maybe cap the numbers at, it's calculating correctly to right here, I think. Let me take a screenshot of that, and then we'll do the next question. I think people are asking chapter 15. So let me see the normal. And this is calculated correctly. Because if you notice, the T is a little bit bigger. So this is just like super particular. If you notice that, and then notice the 639, the T is just a little bit bigger still. It'll always be a little bit bigger. No matter Z, T will always be a little bit bigger than Z. But with so many crazy amounts of degrees of freedom, the curves are basically identical. You'd have to carry it out. And also, it's not 1.96 technically. I always like when a statistician says to me something like the Z-score for 95% of CompStrol is 1.96. I actually lost points in a class because I literally put 1.95996 while solving a problem. And the teacher told me I put the wrong Z-score. So I still remember that because she was like, create a 95% CompStrol, use the correct Z-score, whatever. We had to memorize them back then. So I put 1.95996. She was like, no, it's 1.96. And I was like, no, it's 1.95996 if you care more decimals. And they're just like, this guy. Anyways, let's do some chapter 15 right here. I was that student. I still am that student, I think. Last bit of Starbucks. Some chapter 15. New stuff going on. Chapter 15. I got a load of teams right here. See if my teams are doing anything. My teams are up to. What are my teams up to? Chapter 15. Assignment Manager, Chapter 15. Mobile alerts. Oh, might have something about jobs for students. Wait. Oh. Cool. Got people working on jobs right here. Do you ever want to talk about jobs with students or in the future, especially if you're hearing this now and you get a job? We'd love for students to come talk about jobs. And got some cool stuff in the email, looks like. And Taylor wanted homework 10 and 11. I went to the quiz. Okay. So Taylor about to do the chapter 15 homework 10 and 11 question. Chapter 15 homework. Questions 10 and 11. Okay, let's do it. Here we go. Chapter 13, homework 11. Yeah, Elaine, good to see you here. We'll throw you 100 points. Okay, we'll do that one next right here. Let me mark that. Chapter 13, homework 11. And thank you for being here. We should be doing that in about 15 minutes, I would guesstimate. My guesstimate is 15 minutes. So you can check out this one, and we should be back to those in a moment. So this is... We are here at 5513, Stat 201, Chapter 15. 15 homework 10. Okay, let's do this right here. And I've got your question marked. Thank you for being here. And so here, according to the Census Bureau, 18.1% of the people in the United States are Hispanic or Latino origin. One county supervisor believes her county has a different proportion. Because think about this. Are you Hispanic is a what question? So think of a C word right here. Are you Hispanic is a what question? She looks at the most recent survey data with a random sample of this sample size and found that 58 are this. Great job, Jesse, right there. Categorical. And found that 58 of them are Latino. So when you think about this, what is the notation? I already gave some of the notation right here. I already said that this is sample size. And then what is that? It's usually where people get stuck. You always want to identify your notation, and then we'll talk about what this is in 1 second. Great job, Jesse, right there, because this is P naught. So interestingly enough, we write the null hypothesis that the null hypothesis states that the true proportion is equal to the hypothesized, and all we have to do is just plug in that value right there. Just plug this into here. And X, yep, that's X. That's the amount that were Hispanic out of the sample. So once you get X and N, what do you calculate now? So don't even look at their questions. Just think about, well, I have X, 58 out of the 488 were Hispanic. So what should I calculate now? Once again, always think about, well, what do I have and what can I do? I know that 58 out of the 488 were Hispanic. So what could I do with this? What could I do with this info? 58 out of the 488 were Hispanic. P hat, yeah. So now we can figure out, and this is just the proportion in your sample. So it's X over N. And then we learn that from our sample, remember, this is just like, oh, well, we can calculate that 58 out of the 488 are Hispanic and 48. So there's the proportion. Exactly. Yep. So we know what P hat is. And this is the sample proportion, not what we are hypothesizing. So she believes, so be careful right here. She believes there is a different proportion in her county. So if she believes the proportion is different, we only change this right here. And her alternative to what they're telling her is that it's not equal to that. And look at what we've done, and we're just going to plug in this number right here of 0.181 because that's the hypothesized proportion. Look at everything we've done, and you know what we can actually do? We can solve the remainder of this question because we know the equation that the z equals to p hat minus p naught over p naught q naught. So what are we missing right now, Jesse, that we haven't solved for that would be quick and easy to get? We know p naught, right? So guess what we also need? We need Q naught. So Q naught is just 1 minus P naught. So we just take right here 1 minus P naught. They're just complements of each other. And there we go. It's Q naught. So now we know Q naught right there. Exactly. So we're just going to plug in the numbers down here. The top part of this equation is just a difference. How far are these numbers away from each other? But how far they are away, that distance needs to be standardized down here by the standard deviation. We talked about that earlier. And the standard deviation is going to be the following equation, P naught times Q naught over N square root. And so we plug in the numbers right here to get the standard deviation, and we're going to solve for the z-score. So all we're solving is a standardized difference on the bottom. Or we're taking the standardization of the difference using the bottom. There's the standard deviation. That's the bottom value I just calculated right here. That's the value there. Let's take the difference up top between the numbers and subtract. There's the difference. That's the top right there that I circled. We divide by the standard deviation. It's going to be about 3-ish, 3.56. And here's the thing, Jesse. I bet you can figure out the p-value, because this is the z-score, right? I bet you can figure out the p-value without an applet. So don't use an applet. Tell me the p-value of this is going to be very, very close to what? Because we landed all the way over here. And when we do a does not equals test, we shade both sides. So the p-value is going to look something like this. The p-value is going to be very, very close to what? The p-value is the probability or the shaded area. It's going to be very, very close to what? Because we're all the way at the ends of the curve. We'll find the exact value here in a moment, but I think, oh, well, so I get where you're going with that. I think I see why you got that number, because you're thinking if you go out 1, 2, 3 standard deviations, 1, 2, 3 standard deviations, outside of 3 and -3 is total 0.3%, or as a decimal 0.003. But think about this. You ready? Are we further than 3? You guys see the number behind me. Are we further than 3 or are we closer than 3? Are we further than 3 or closer than 3? We're like further out, right? There's the z-score behind me. We're further out. So our p-value should theoretically be wider than this value. Our p-value right here should theoretically be wider than that p-value because we're further out. So here is 0.003% of the area, and we're further out, so it'll be smaller, exactly. We're going to find the exact answer here in a moment. I've done a little bit of a quick solve on this, but maybe it's a more high-level solve. But we basically worked the question. What are we doing here? We're doing a one proportion z-test because we're testing one proportion with a hypothesized proportion. Check the appropriate conditions. Random 10% success failure. So now they are actually having you find the successes and failures. They were a random sample. Okay. There we go. And here's the NP naught. This is actually really good that they're actually having you do NP naught for once. That's P naught right there, timesing it by 488. And do they want it rounded? Round to 1 decimal. The expected right there. And we could subtract that out of 488, but we can go 488 times 0.1819, I believe it is. And then this right here. And that was Q naught right there. So if you're wondering what mathematics I'm doing NP naught and Q naught, which is equal to 488, and times right here the P naught, which is 0.181, and the Q naught, which is 0.819, which we found earlier. That's just make sure you mark your notation, and then you can see they're literally saying NP naught and then Q naught. And so as long as we didn't mess up any of our decimals, we should be good. It says to 1 decimal place right there, and we are good. And if you want to check your work, both of those numbers should add up to n, because you're saying how many expected successes are there and how many expected failures are there, and it should add up to total sample size. Thus, the conditions are met, and it is appropriate to do the normal curve here. And so now it's actually, wow, they actually show you. And so think about this. Where should the null, if the null is true, it should be at the where of the curve. And we talked about this in class too, so I'm really glad a lot of questions do this. If the null is true, it should be at the where of the curve. So don't even look at their answers yet. If the null is the truth, it would be at the very what of the curve. If the null is the truth, it'd be the most likely thing to see, so it should be at the where of the curve. Because if we believe the null is true, then we should probably see it quite often from random samples, the middle of the curve. Well, that eliminates right here this answer over here with 0.181, because that's what we saw in a sample. Our sample proportion was 18.1%. So that is not, wait, no. That is the null. Dun, dun, dun. Ah, we were much lower. So this is the answer. Wow, they're throwing tricks right here because the null is 0.181. And so that goes at the center of the curve. So they're throwing tricks doing the old, like, the right answer is the only one that, you know, when you look at the similarities, they're tricking you. So we did land below, but we do shade both sides. So here is where P hat is, and this is a P hat just as extreme on the other side of it. So that's where a P hat just as extreme would be on the other side. So that is going to be our answer right there. Calculate the Z statistic. We did that earlier with 3.56 to 2 decimals. Check out the work at the start of this question for 3.56. Uh-oh. We made a math error. Let's check it out. Okay. What did we do? My math today. What did I do, Jesse? I cannot math. That looks accurate. I want to review the tape. Please tell me it's not because of a decimal that they carried, that they're saying the proportion is 119. Oh, no. Jesse, no. Do you see it? Oh, come on. No. Really? Really? This is where you get points back. Do you see it? I can't round today. It's 3.57, I think. I literally just didn't round this properly. Or I made some other error. Are they using 0.119? And that makes a little decimal difference? Thousand points if you see my error. I know what it is now. Let me point to it. I can't believe today I'm just off my game. Look at the equation. And then look at what I noticed when I redid my graphic. And then the answer is on the far left, the correct answer. And I'll rewrite this here in a second. But 1,000 points if you notice it. I was able to deduce the p-value. I noticed it when I did my graphic. But take a look at the notation, and I made a mistake, which then I noticed when I went over here, which I should have then noticed that and been like, oh, yeah, of course. So look at my notation very carefully. It's all those 1s and 8s. The issue, give it a few more seconds right here. So it's definitely a notation issue. Because remember, we're below average. We're below average. See if anyone catches it while I'm saying it. You got it, Jesse. Yep. That's exactly what I did. So simply the answer. So theoretically, all I have to do is what? So theoretically, I'll show the math that is correct, but theoretically, all I have to do is what, since I flipped them, which I did notice when I redid my drawing right there. But all I have to do theoretically is what? Like, I don't have to resolve this. Just understanding, because P naught is this. Flip them, but the answer is just going to be what now? Since I flipped them, the answer is just going to be, remember this over here? So the key is that I then marked that we're actually over there. It's just going to be negative. Because I was like, wait, why are we over there? Oh, yeah, because we fell below. So that's all it was, is I forgot the negative, which is important. And this is where we can figure out the p-value without the applet, like I said. So I was so focused on figuring out that p-value without the applet. I mean, I would know by looking at this that she has evidence of a difference. Let's go show that on the applet, though, and how to get it. So once again, make sure to go over here to the apps. This is where our knowledge of z-scores can come into play and help us figure out answers without the apps. So it's always kind of neat that we can get answers without the applet. Here's your greater than test, your less than test, your confidence intervals, and your does not equals test. So make sure you know what each button does. Now, when you are doing confidence intervals, you will use the between, and you will use the x from a p-value, which is going to give you the percent of area. When you are doing tests, you will need to go right here for find p-value using x, because you're going to enter in the values of what x is and get the probability. We want to go to the outside. We want to grab our z statistic, go to the positive, go to the negative, and make sure they're z-scores, and carry to 3 decimals. And so it was basically 0. We would have gotten it right if we put in 0 also, and I just rounded it up a little bit too much, but 0 was basically the answer. And once again, look at our drawing to see that we drew this out here on the bottom to show that there is basically no area outside. The outside test is going to show you the area outside the numbers you put, and it's used for the does not equals alternative. This is a very important thing to know right here, that the sign of the alternative denotes which way you shade. Had we done a greater than alternative, we would be shading to the right of wherever we landed for the z-score, and it would look something like this right here. Not for this test, but the sign of the alternative. This portion right here, and the researcher's question is going to indicate the sign, is going to indicate what way you shade. She wanted to see if it's different. That was the does not equals. But do remember, if it's like below, you will shade below, and the sign of the alternative indicates what way you shade. Are they testing greater than? Shade above. Are they testing less than? Shade below. Are they testing to see if it's different? Shade outside the 2 regions with the positive and negative version of the test statistic you find when you run the test right here. And so, yeah, good stuff. Good question. Since the p-value is low, there is evidence that it is different. I think that's right. Yeah, the p-value provides sufficient evidence. I do want to point out, let me go back to this question here real briefly, and then we'll do the next one. And I think we have just enough time to do the other question mentioned in the chat. I do want to point out that when you get to the final part right here, Jesse, we haven't done this a lot in our class yet. You have to write out the interpretations on the test. So I'll say this one right here because we haven't practiced it, but you would say, with a p-value of 0.003, I reject the null hypothesis because it is below 0.05. That's your assumed alpha level. This means I have evidence for my alternative. You can say I reject the null that the true proportion of people that are Hispanic is equal to 0.181. I have evidence that the true proportion of people that are Hispanic is not equal to 0.181 for this county. So with a p-value of 0.003, I reject the null because it's below my alpha level of 0.05. This means I have sufficient evidence for the alternative hypothesis that the proportion of people that are Hispanic in this county is different from 0.181. And there you go. You can say reject the null that the true proportion is equal to 181. So that is what you'll have to do for the test. And that's usually some of the hardest questions for people to write out. But once again, it's just going to come down to practicing saying it in class, where we say what is our p-value, what is our alpha, did we reject the null, and did we have evidence for the alternative, and also state what the null and alternative are. So we try to break it down into parts, and we practice that, but you will write that out. So don't just look at their answers. Think about how you would write it out. And I want to do 2 more here, so that's what we're going to do. So when we write the null, we got 1 more right here. Let's mark this, and then we got 1 more after this too. How in the world? Sometimes I just can't get questions right. Stat 201, don't reverse your numbers. Chapter 15, homework, question 11. When you write your null and alternative hypothesis, you want to mark your notation to begin with. And this is our hacks method that we're practicing in our class. So when you get this right here, the things we need for the null is we first need to figure out, are we doing one of 3 things? Testing a proportion, a mean, or the difference between means. That is going to determine how we write our null hypothesis. This right here is the age at which men are first married had a mean of this. So are we trying to figure out p, mu, or a difference between 2 means? Which one of those are we trying to figure out? P, mu, or a difference between 2 means? The more you practice this right here without looking at their answers, the better you get. So what are we trying to figure out right here? Are we trying to figure out the proportion of something, the true mean of something, the true proportion of something, the true mean of something, or the true difference between 2 means? So it seems to me that we are trying to figure out the true mean. Mu, yep, because that's true mean, right? Mu is true mean. Great job, Jesse, right there. So that's going to be the null hypothesis states that the true mean age of marriage, and then the null always has the equal sign, is equal to the claim. Now, the only thing that changes when you write the alternative is going to be the sign. So we just have to think, what are they testing? What is their claim? It is suspected that young people today are waiting longer to get married, so the true mean age of marriage is greater than, I got married at 40, so I'm an outlier right there. So waiting longer right here is going to be important for figuring out the alternative. And so equals right there, and greater than is going to be the alternative. And that's how we know the information. Now they go to the conditions. Condition 1, randomly sample the individuals, which goes to independence, like they need to be independent to be random. Condition 2, less than 10% of the population is sampled. And condition 3, nearly normal. I don't think we don't have the data right here, so we'd have to assume these. Independence can be reasonably assumed and satisfied, and the nearly normal condition can be reasonably assumed. I do not like these answers. And satisfied because how many it doesn't even say how many we talked to. Oh, they talked to 40. They talked to 40 right here. There's the sample size. I don't think all the data's in yet, though. We can try to do that, Jesse. We don't know the size of the population. The population is normal. We don't know that. It's a medium sample size. I'd prefer them not say this is large. That's not small. It's medium small. Therefore, using the student T seems reliable. Should be reliable. That looks correct, yeah. Don't love the way they phrase this. Don't love the way. And so with this right here, they're now basically asking you the equation and standard error S over, oh, look at this. Okay. Mu equals this and standard error equals this. Oh, and then they say normal down here, so that's definitely wrong. They should put over square root. So they're kind of showing you the calculations right here. This is the equation to do the T. So they're walking you through this a little bit here, and they want to know what mu naught is. So mu naught literally is the hypothesized value, and that is mu naught right there. So make sure you mark your notation. That is mu naught right there, which literally goes in this portion. So you can write the default format of mu equals mu naught, and that's what we plug in for the null right there. We put the mu naught value in. So with this, we need to plug in the value of mu naught equals the hypothesized mean. And then over here, they have the standard error. And the standard error, we've already written it out a few times today. The standard error is s over square root of n. So it's kind of weird to me, and this is a t interval. But if you'll notice, the t interval uses the same, and there's a lot of similarities between intervals and tests. So that's the t interval right there, which is the estimate plus or minus the t statistics times the standard error, which is s over square root of n. The test is the sample mean minus the hypothesized mean over the standard deviation divided by the square root of n. And be careful here, this is equal to a t, but these two t's are not the same. They're similar, but they're not the same. So those are not the same value. This t on the bottom is a standardized difference, where we have the difference divided by the standard error, and the t up top is relative to a % confidence. So this is picked based on how confident we are to make the interval, and this is figured out by how far away was the sample mean from a hypothesized value. So this t does not have a star on it because it's not relative to a % confidence. It's just the difference between these two numbers standardized by the standard error. And then this right here will be based on level of confidence. So be very careful. A lot of people think if you solve this t, you've solved that t. No, this t has a star for a reason, relative to a % confidence. So they want over to the square root of n right here. So we need to take the square root of 40 and solve that. And that's what they want. How many decimals? Type exact answer. Oh, use radicals. Haha. Radical square root 40. There we go. This is the following t distribution with 39 degrees of freedom because the one sample t has n minus 1 degrees of freedom. That's a pretty good way of doing it right there. Pretty good way of making you understand the notation. This is the standard error, s over square root of n. So they're saying the standard error of the sample mean is this. Decent. The mean in our sample is this. And so let me think, that was like 6, right? And the standard deviation, where's the standard deviation? Where am I missing that? Am I missing the standard deviation? Oh, there's the standard deviation. So that's about 0.9. So 0.9 right here. That's a difference of 1. That's a t-statistic of about 1. So the p-value, this is a guess. This is a guess. 100% a guess. It's very hard to guess this one. There's a guess. And we're not correct. Let's see how close our guess was and then see why I guessed that. Okay. So, it tells you the t-statistic. Holy mackerel, they just flat out tell you the t-statistic. Well, I thought the t-statistic was 1. It's actually smaller than that. Now we're closer. Okay. So where do we need to go with the t-statistic of 1.193? They literally solve the equation for you of the sample mean of 24.3. That was given right there, minus, great job, Jesse, minus the hypothesized mean, and then it's 1 higher. They take 5. We'll take square root of 40, and 5.3 divided by this, and then they go 1 divided by that. There's the t-statistic they found. So maybe solve the equation here that they're doing, and then they take the t-statistic and they bring it over to the apps. And here's the thing. We have to go to the above, and then we have to put in our t-statistic, and then we have to put in, because I'm on the wrong one, go over here. We have to go to above, and then we have to put in 39 degrees of freedom, and the exact answer is going to be, it's 12 on the dot. It's 12. So we were kind of close. So if you notice here, the answer is 12%. Here was my guess at 14%, but it is 12%. That should be right on the final guess right there. But it was 12%. I'm able to decently estimate these a lot of times because I know about where we're at. We're a little bit higher than 1 on the T curve. So think about this. If this was the Z curve, you would probably say it's a little bit less than what %, Jesse? So think about how I'm doing this. If we're above a Z-score of 1, then you'd probably say it's a little bit less than 1. So that's why I was guessing like 14%, because T's are basically Z's. So when I'm like, oh, we're at 1.19, 14% or so. Exactly. Is it making more sense how I'm guessing these? I'm like, oh, if that's the T, well then 16, I don't know, 14%. So you're not meant to guess these, but I want you to understand where these numbers are coming from and how chapter 5 actually relates to this. So you can go to the applet to get the exact answers, which we should do. But the reason I don't really care so much is because when I run tests in software, it gives me the p-value instantaneously, just like that. And I can just change the hypothesized mean here to like mu equals 70, and it'll do a different test for me. That should be unused argument. So when I run it in software, it just literally gives the p-value right there and gives the alternative. So really just knowing what you're doing and why is what's important, because the software will oftentimes do the calculations for you. Explain what it means. The p-value is the probability of seeing a sample mean, of getting a sample mean of 24 or older. Right here, of getting a sample mean of 24.3 or older, because we're testing greater than, from natural sampling variation, given that the truth is the null, given that the null is true. And that's a pretty good interpretation, because this is, oh, they're giving one more. So the p-value is the probability of our results or results more extreme. That's literally the phrase, our results, which was the sample mean, or a result more extreme, due to random variation, given the null is true. That is textbook interpretation. So my Pearson gets an A+ there. The p-value is the probability of our results or results more extreme, given random variation of the null being true. And so the last question right here is, do you reject the null? Well, alpha right here is the point at which we reject the null. And when the p-value is low, we reject the null. When the p-value is high, we just let it fly. So we do not reject, and there is not evidence for the alternative, that it is greater than. Make sure to link this back to what you were investigating to see that we're looking for evidence greater than. And if you do not reject, there is not evidence. If you did reject, then there is evidence for the alternative, because you're saying, I give up my null hypothesis, I'm rejecting it, I'm going to now believe the alternative. But we are not giving up our null, because we do not, hey, Sloan, what's there? Good to see you here, 100 points, Sloan. Because we are not giving up our null, we do not have evidence for alternative. Rather, in order, it would be, you did not have evidence for your alternative, so you are not giving up your null hypothesis. And good stuff right there. I think there was one more question from a student. Like, Jesse has a question too. But we also want to do the last question from the student who swung by, and they said chapter 13, homework 11. Let's go do that here real quick. Thank you so much, everybody. Those are really good questions, like understanding those and knowing how to solve those. Once again, we want to be able to solve all these. Okay. That's a really, if you can solve that question, understand the steps in it, you're doing really well. I know it's makes the test easy. You get to the test, you're like, I've done this so many times. You just finish the test and you're like, sigh of relief. Sigh of relief when you get done with the test. You're like, I got an A in the class. Best Starbucks looking drink ever. Chapter 13, homework. I think there's an interpretation one. Okay. Ooh, it's a confidence interval one. Let's check it out. Need to remark the time. It takes me longer than I thought. 1:24, 23. Okay. Here we are, and what is going to be the number one way to solve all this out? We need to add in some new levels here. What is, let's add a Sloan level real quick while we do this. Tell me what the Sloan level should be called, and we'll add it right after this question. Class president level? We'll add in a Sloan level here. So if you are solving this question right here, a lot of your questions all boil down to notation.
Notation, brother.
It's all about that notation. You get the notation wrong, like I've done once or twice today, you get the question wrong. It's all about that notation. So let's do a quick solve of this, and we'll take a few other things. You nominate, name the level, class president level Sloan, or we got a sample. How many people donated from that sample? That is X. Once you find X and N, you instantaneously calculate what? Don't even read their question. You find X and N, you calculate what? Great job, Jesse, right there. Related to a Z star. And true So this is actually P. Be careful, we're not really going to use this yet. We're not really using that. That's a claim. That is technically a P naught. So we could do a hypothesis test on it. Actually, that's a claim. They don't know it's true. A member thinks this is the truth. So that's a claimed truth. Yeah, let's do that here. We'll do it here at this, Sloan. So that's not really going to be used. Like, we're not going to do the test, but we could see that we wouldn't reject it. So we could actually run the test on that if you want. It would relate back to the problem we just did, but that's not going to be used when making the interval. And so Jesse already said that this is P hat. So X over N equals P hat, and 4781 over 100,000. There we go. Yep, here we'll do that here next. Then once we have P hat, we get what? Once we have P hat, we get Q hat. Q hat is 1 minus P hat. So, wrong. There we go. 95219. There we go. And so now it wants a 95% confidence roll. Well, we already got everything. We've got all our components. We go right here and we go P hat. Oops, I don't know why I'm writing equals. If you're wondering how we got the Z star is always 1.96 for 95% confidence. Make sure to go to the apps right here. Under the apps screen, we'll go over here and we'll pull up the normal curve. On the normal curve, we will go to find a X using a p-value. We'll go to the between for confidence rolls and enter in 95% confidence. And it's 1.96 or more classically 1.95996. But more people just say 1.96. So baseball, good stuff right there. Do you play baseball for UT, Sloan? I know Julio Bourbon, who is a huge supporter of UT baseball and just an all-around awesome dude. But he's just great. So Julio, shouts to Julio right there. He's just one of the nicest people I've ever met in person. Like, just like I met him, he's like, "Hey, how you doing?" I was just like, "Hey," he's just giving me a big hug. Like, I don't know, that's one of my favorite. Like, I don't know, just met him. He's like, "Hey," like, hey, nice to meet you. It's like, but he's just really nice, really. Just I love people who bring a lot of positive energy. Like when you just like you get this like energy high from being around them, where you're like, man, I just feel like better just like seeing them. Just like that's really great right there. And so one of my favorite people right there. Just and he was so like, if you meet someone who's like done professional sports or something, no on the official team, we have a club team, awesome, good with the club team. Then I played QB from high school, quarterback, wow, Sloan. Like. I think a lot of people realize, or a lot of people understand as I solve this question, that we're all just people. We're all just people. No one's like inherently better than anyone else. Like the fact that Julio played for the Texas Rangers, and went to the World Series, did all these things right here. Good to see you, Abigail. Julio, you can tell he doesn't look at that as like, oh, I did this, I did that. And so, you meet someone who's like been to the World Series of baseball and you're like, whoa. And he's just like, hey, good to meet you. And you're like, good to meet me? Me? You're like, you're the one who's been to the World Series. It's kind of cool meeting you. I'm not even a big baseball fan, but you don't usually get to meet people who've played in the World Series that often. And, he was just nice. And that's really what matters. And so it's really neat, It's nice when people just treat people like people and everyone kind of values everyone in our society. Photoshop, oh my God. So that's what I appreciate is when we treat each other with respect. And, when I meet my students, my high school resume, QB, pitcher, third baseman, and valedictorian. Woo, Sloan right there. Great job. It's about just treating each other with respect and valuing each other because we can all help each other out. So, it's funny. This is a total tangent in the conversation, but we were doing a Pokemon Go raid one time. I'm just solving the equation, and in the Pokemon Go raid, this guy was like level 18 or something. He was like, I just started, and we were like, well, you should join the raid with us. He's like, I don't know, I probably won't help. And we beat the raid with like 3 seconds left, and there was like 4 of us, and we were like, dude, if you weren't in this raid, we wouldn't have won. And the raid was ending. If you know Pokemon Go, we were like, no, like we beat it with 3 seconds left. If you weren't in this raid, your little extra help totally, you know, he was like, well, I don't know. We were like, come on, you got your daily pass. You know, if you want to do it, do it. And he's like, well, not gonna be much help. And we were like, come on, let's do it. So yeah, so that's Sloan. Oh, academic. Let's not add weapon in there. Let's add class president level or something. I'm always worried about maybe someone in the future seeing something and being a little confused. I do like it. Like, I think it's pretty funny. But I'm always like, one person gets like mad about something, you know how it is. It's like one person would be like, what the heck? And then it's like, uh-oh, 4.913. We're just adding and subtracting the numbers right here. It's all about that notation. Yeah, that's the issue. And you just have to be very and you know, obviously we should acknowledge what the one person thinks and says. But obviously there's context to what Sloan is saying right there, and I take no offense. And then unfortunately sometimes when you go into the future and someone doesn't know any context to it, it could look very like, what? Like, and then I'm always, well, here's a funny story. I used to, a long time ago, not mod up my students, so I didn't really know who was students. And we do have visitors who come to the stream, and I do have a few of the visitors modded. So we actually have people from all over the world. We have people from India, from Germany, we had Russia. We've had people from all over the world come and learn statistics via these videos. So hey, if you're watching this video now, doing some stats as I kind of just ramble about stuff at the end of office hours, feel free to always ask your questions. If it really relates to the class, we always handle it. Or if we're kind of in a sort of time where we're just chilling right now, we might also talk about it. So what happened one time is this one person was kind of making fun of somebody a little bit. And this is 3-4 years ago now. So they were kind of like making light fun of somebody. And they were just like, oh, haha, you're so wrong or something like that. And I was like, oh, don't be mean or something like that. And they kept doing it. They just kept on making fun of that person. And the person emailed me and they said, hey, I don't know that person. They're like, I don't really like, because I've had friends make fun of friends on here. I've had roommates and they're like, oh, they're my roommate. And they'll make a joke on them or something. And I'm like, oh, well, be nice, because that scenario right there made me realize like it might just be some random person on the internet. And so I'm always telling people to be nice, which I do want people to be nice. But they were like, I don't like this random person on the internet like cracking jokes on me. And I was like, okay. So I just banned that person. They could be watching right now for all I know. I checked and they weren't, and that's why I started modding students during class. So the people who are modded are usually like trusted individuals. So if you have a name that's in blue, you have a lot more trust from me, and it just helps me see who my students are. So when you come to a stream here, Jesse, like if someone were to, like, I would know who the person is because you've had to come to class. And so our class links are in unlisted videos. So that's why some people say, I can't find class. None of the classes are posted. I'm like, oh yeah. Yeah, exactly. And so you get a little more leeway. Do we believe 4.7? Mm-hmm. It is in the interval. Yep. And there we go. What's really cool, and here's how we would do this in real practice. So you saw how long that question took us? Here's what we would do in the real world. What was the proportion right there? It was, what was the numbers? It was 471, 4781. And there's the answers. Yep. Intervals calculated a little bit differently. And then we could also test if we would believe the value of this right here. So there we go. There, I just solved the problem again. And, ooh, is that not in the interval? Wait. Dun, dun, dun. Wait, the alternative... Wait, no way. Is it the same? And does it do the calculation a little bit differently? Oh, there's the p-value. How am I missing things? My mind today. There's the p-value. All these p-values. So the p-value there is high, so we would believe the value. The value is also contained in the interval. And we would just enter in the value of x. We'd enter in the value of n. We'd put in the hypothesized value. We'd see that we do not reject it. So we cannot reject this as the true proportion because the p-value is high, higher than 0.05, which is the level of alpha commonly assumed. And we just literally ran the hypothesis interval and the test. This uses the chi-squared interval, so there might be small decimal differences. So I've tried to check some of these questions. 4.65, let's see right here. Actually, that would solve. So here, watch this. If we go back to the non-completed problem, 4781. Oh, it's the same. So literally, if we had done this right here, and we could actually store this as x, and then take x and take confident, And there's the confint. Can we take round on it and round all the info to 2 decimals? Let's times it by 100. And there it is right here. So now we just take the answers here. We drop them in. There's that answer, rounded. We go to this answer, rounded. And there it is right there. There's the values. And is 4.6 plausible? We can run the interval right here, testing 4.6. We'd reject that. So actually we stored the result, so we'll just run the result again. But since 4.6 is not contained in the interval right here, we would reject that. So I already knew the answer because it's not in there. So is not plausible because the interval does not contain it. Hence we would reject it. Does that make sense, Jesse, right here? This is how confidence intervals and tests are connected. Like I knew before I ran the test that since the value is not contained in the confidence interval, we would not believe that value is true, because when you look at the confidence interval goes from 4.65 to 4.92. So hypothesizing that 4.6% is true would be rejected because it's outside the 95% confidence interval. And a 95% confidence interval assumes a 0.05 alpha. So let me ask you this. This is sometimes on the test here, and then we'll look at the distributions. A 98% confidence interval, this is a chapter we'll be doing next week. If you use a 98% confidence interval, that is mathematically the same. So this is the confidence interval with 98%. That is mathematically similar to running a what-tailed test with what alpha level? And the answer is visually right here. So a 98% confidence interval is mathematically the same as running a what-tailed test with what alpha level? Which means we're doing a does not equals alternative. So what would be the alpha level? The alpha level is the percent of time we would reject the null. It's your type 1 error rate. More on that next week. So the key is that they're complements. So the confidence interval is connected to the test because a 98% confidence interval is related to an alpha of 0.02 or 2% alpha. And it's related to the two-tailed test because the inside is the confidence interval and the outside is the hypothesis test. And so if you just change this to 5%, that's why a 95% confidence interval is related to the 0.05 alpha level. So a lot of times people make 95% confidence intervals because then you can run a two-tailed test. Does that make sense there, kind of mathematically, Jesse, that the confidence interval and the test are related? So that's when I run this down here, I can be like, oh, it's outside the interval. Well, then I would reject it on the does not equals test. And so literally I'm running a does not equals test by putting a hypothesis value right there. And that's just how quick we do statistics. Like we really don't work things by hand, but we understand what the results mean and how they're connected. And really, frankly, you can just look at a confidence interval to look at all values that are possible. Let's look at those values on the test. So you're in class, the earlier class or the later class? The earlier class is at 2:30. The later class is at 4:05. Which class are you in, Jesse? And you might have to pull up the distribution from the video. Or if you link me, if you've got when I showed the distribution, I got to verify it's me logging into which class? 4:05. Oh, yeah, we still have 122 left to be graded. I think the grader hasn't started yet. And they're supposed to start. And so I need to talk to them and I need to say, hey, remember it's a week and we've already gone past that. And so we really want them to finish the grading. Let's go to the quiz statistics here. And then we want them to do the grading correctly, not just quickly. So quiz statistics are coming up. I don't think it shows anything that we shouldn't show. I'm just going to wait for it to populate the screen. You have to wait. It takes a while for it to populate. It's like doing calculations in the background. I don't know why it doesn't store it. Yeah, I mean, I guess because it would have, it's anytime you populate it. So there are hundreds. Mm-hmm. The average is a 68 right now. Whatever, was it a 66 before? Surely. So we should be near. I think a lot of classes have like a 70 average. I could go look at that right now. Let me see what the averages for the other classes are. And if you can remember what the average was previously, Jesse, that'll get us an idea because we should get another 1/3 increase to whatever the increases were. Some of the class averages are, one class had a 72 average. Another class had a 68 average. They do have some zeros in there, though, which they should remove those because zeros means someone didn't take it. Another class had a 69 average. So 69, 68, 72. So can't remember. Let me look at our other class too, and then we'll end with that. Okay. We did the 405. Let me see what the other class is. Oh, the average was a 63. So we might get another 2 points. So I think we did all right. We're not the highest. I always want us to be the highest. Yeah, so the average time won't change. So yeah. Well, we might have had, I think few issues, like, which once again, please contact me if there's any issues. Here's the other class, quiz statistics. Oh, I think we had the higher average, right? I think of the two classes. So I've got the morning class and the afternoon class right here. I think, wait, this would be the morning class. Okay. Oh, thank you, Jesse, right there. Oh, wait, Jesse, we probably need to, I'm going to remove, wait. Can you delete that message really quick, Jesse? Delete it real quick. If you click over it, you can delete it. Thank you so much. Yeah. Thank you. Whoa. I need to look at how okay, so I need to look at, this is the morning class. We'll find out. I don't want to say what he will or won't do. We'll find out. I don't want to take bets on it either, because if I bet and I'm wrong, people will be like, you said it would probably be this. I have an idea of what I think will happen. I don't want to say it on stream though, because just because I think it linked to the class and their unlisted streams, and it might have linked to the playlist or something like that. So I think it was a link to like the unlisted streams. Does that make sense, Jesse? So and thank you so much, Jesse, 500 points. Because I think those were the unlisted. Does that make sense? Because like people can't normally find those. Now that's deleted. Yeah. Oh, his office hours? Oh my gosh, Jesse. Jesse, I got 3,000 points. Sorry, I didn't click it. Yeah, then 100%. Yeah. 100%. Thank you so much, Jesse. 1,000 points. Yeah, 100%. Yeah. So I didn't click it, so I didn't know what it was. I was just like, oh crap. So I was trying to remember if I showed it during class or not. So Jesse, you were in the right. Brian was in the wrong, as the usual. I was like, oh no. See, that's the thing, is I'm always like double, triple checking. We've actually never had issues. Has anyone ever heard of like when people like Zoom bomb a class? Did anyone ever hear about that in the past? Like when people would do Zoom, like when they would have teaching via Zoom, and a bunch of like YouTubers or TikTokers or Instagrammers or whatever peoples or Facebook Livers would like Zoom bomb a class. It's like, I've never had issues with that because my streams are like, you can't really get into them. And then also I can turn on modes where like people can't chat as much. And then YouTube has like more restrictions than what can be typed in like a Zoom chat. Cause I don't think Zoom chat even restricts what can be typed. So we've had like one issue that was really bad that I don't even like to talk about. Like one time in like 2020, I even like put out a statement like where we had people trolling us. So that's why, and you don't mention the trolls, because if you talk about trolls, then you're likely to get trolled again or something like that. So I'm walking on thin ice right here by even talking about trolls. It wasn't super bad. I was just very unhappy about it. Like it was very bad, but like we handled it well. I'd say that, like in terms of like, I think it was handled well for a bad situation. It was just a troll, someone being ridiculous. Yeah, exactly. And that's the thing is, so I've talked about this, how a lot of teachers had to teach online and they were not used to it. I've been teaching online since 2015. And the problem is a lot of teachers, I bet you there's a lot of people who got trolled online, and then they didn't even see the person in the chat. They didn't even see the person in the video. So there's probably been a lot of trolling of teachers that they don't even see. So the students are like getting distracted, which I mean, like there's funny trolling and then there's just really bad trolling. So it all depends. Like even I saw some of the videos and it was kind of funny. And then I just thought, man, it's a bummer that people really don't know how to teach online. And I don't mean that in a bad way, but you take all these educators who are teaching in person and they've only taught in person, and then you put them online and you say, okay, now teach on the internet. Well, they're not used to that. So it's not completely their fault that they were thrown into a teaching modality they've never done. I'm really lucky, like I said, that I've been teaching online since 2015. So when COVID hit in 2020, COVID-19, but we switched in March 2020. Then I was like, oh, I've been doing this for 5 years. So for me, I was like, I know how to do this. I know how to teach online because I was already teaching half my classes online anyways. So there were no complaints about what I was doing or what was going on. And then we had people retire. People were just like, I don't want to teach online. It's totally different. So I am excited next semester, Sloan. And so swing back. We need to make your level here, Sloan. Next semester, I will be in person, and I'll be on campus in person. I'll be back in like 2 months. We're in April right now, right? March, April, May, June, 2.5 months. You start getting the things here to go online or go to campus. But yeah, I've got check out my points. I've got 11 million points. Started giving away a lot of points lately. Let's go here. Sloan, class president level right there. I'm at the meme tier level. This is the level we give people when they've gotten way too many points. You have to get 10 million points. Where is... Oh, people only have 100,000 points? Did I not delete my points? I know, right? There we go right here. Okay, let me make your level, Sloan. What do we say, class president level? We said... And so we'll go 120,000. 120,000. And Sloan class president level. Sloan class president level. Okay. That's how many hours I've been streaming online for the last 2.5 years. So it's interesting to think about. 2.5 years. 3.5. When did I make MuBot? We used to use Streamlabs to count points, and then I had to download MuBot because I stopped using Streamlabs. So I think 2.5 times 365. There's the amount of days I've streamed online. And so I've been online a total with MuBot active of this. So I've streamed 2.3 hours a day for the last... so that is 2.3 hours a day daily for the last 2.5 years I've streamed. And that would be like not like just weekdays. That would be like average daily, which that's MuBot being active too, because sometimes I forgot to get MuBot active. But yeah. Or maybe I'm not typing in the chat. But I think I type in the chat a lot. So I've been active in the chat for 2,118 hours. Thank you, Sloan, right there. Well, with that, I'm going to get ready to teach some 320. And I appreciate both Sloan, Jesse, and everyone else here. We'll be doing some more later, but great work this week. Practice up. Learn how to... I'm only at 73 hours. No, you're doing great. I wish I could show you all the hours and points and everything, but you're doing great. Sometimes I reset them. The highest student, I shouldn't say what they did, but I wish I could show you this list here, Jesse. You're on the first page of the list. You're at 79 hours. You're on the top page. So you're up there. You're at nearly 60. That's about... I wish I could show you this page because I've reset the hours before, but the people on the top page are... Every name on this page, literally, I know each of these names. Like, I remember each of them. I remember them in class. And it's kind of weird to think like an online class. Like, I don't know. I can't probably say because they're like, oh, this student really attended. Like, I scrolled down. I know all those names. I think I finally see a name I don't remember off the top of my head. But yeah, a lot of these names, I'm like, I remember them. I remember them. I remember them. I remember them. Do a stat set next semester with the points and how they do on exams. Yeah. Well, no, I have done that. And there is some relationship, but there's a lot of variation. There is some. And I've done it. It's hard to do it because I have to input a lot of the data myself. I have to like go get your data because I've asked people to input it and then people input like they put in their points and they put in the wrong data. So there's a lot of data entry errors. So I might do it again, but I need to link those data sets and show. I wish I could do a time series. If Mubot could track your current time in class and then we could watch your grade increase or decrease, but there is a pretty strong relationship. I think it explains like 20% R squared. I think around 20%. So just attending class is around 20% of how you do, but it doesn't cause you to do well. It's being here, paying attention, doing the work. But with that, I'm going to get ready for class. Bye for now, everyone. Bye.